Hey everyone, welcome. The topic this week is expectation. To frame this in terms of the rest of the course, we're still working on probability theory. We started by describing what probability is and in terms of like a population proportion. And then we described how thinking in terms of population data is not always practical or feasible, and how tools like density functions let us describe probability in ways that are sometimes easier to work with. We described independence, which is a way to talk about how different variables that you measure are related or not related in a data set, in a population. And then today we're going to talk about expectation, which, roughly speaking, we're going to talk about several different ways to summarize information about populations. And what we learned about distributions and independence will feed into that. So let's get started and motivate this. Remember, the big picture of statistics probability is we have this thing on this side of the screen here, which is our data generating process, DGP. And you can think of that as a population data set. If you want to be super concrete, you can think of that also as a distribution if you want to be more abstract. You can think of it as R code if you want to kind of be somewhere in between. Whichever way you're imagining this is some source of data, some unknown true source of data. And what you see in the real world is just one data set that comes from this distribution, or that is a subsample of this population. And what we would like to do is to use this data to say something about the population. We do not care, typically, about only the subsample of data that we have. We want to be able to generalize to the population, or to say something about the distribution from which this data is drawn. And so the question that we're going to talk about today is, what is that thing that we want to know? What are some commonly, some things that are commonly wanted to be known? And how do we formalize those things mathematically? So, for example, if we have this population of people who are voting in an election, we might imagine taking a poll. And that poll, maybe we call up 100 people, ask them who they're going to vote for. And we know that the proportion of people who are voting for a particular candidate out of the 100 that we call is not necessarily the same as the proportion of people in the population who are voting for a particular candidate. So in this case, what we want to know is, what is the vote share for each candidate in the population? All we have to work with is our poll data. So this is the number that we care about. There's other kind of more complicated numbers that you might care about. So here's an abstract that I pulled from some epidemiology journal. And you can see here that they're talking about things like conditional risk ratios, effect modification, marginal risk ratio. Each of these are all technical terms that maybe you've seen before. Each of them means something concrete. They're things that you can define concretely mathematically in terms of a population. They're numbers that describe populations. And almost all of these are built on top of an analytical tool called expectation, which we will talk about right now. So what is expectation? It's actually quite simple. It's just the population average of a particular measurement. So most of you have, if not all of you actually at this point, have to have seen the idea of a sample average. So if you have little n observations of a particular measurement, like let's say the height of 100 people, the average height of those 100 people is, you just add up all of their heights and you divide by n. Okay, however many, in this case 100, however many people you have. So expectation is the exact same thing, but instead of doing it with 100 people with your sample, you're doing it with your entire population. So it's imaginary because you never actually measure the entire population, but you have to imagine, what is that number? We're over here we're talking about stuff on the left-hand side, this side of the screen over here. You have to imagine, what is the expectation of a particular variable? What is the value I would get if I could measure this thing for every single person in the population, and then take the average? So here I'm writing out kind of like the idea of that. So remember, we can write a random variable x, like height, for example, in this way. This particular notation just says measure height for omega 1. This is like a stand-in for person 1 in the population. measure the height of person 2 in the population, so on and so forth. Measure the height of the last person in the population. And then add them all together and divide them by big N. So again, when you see a little omega here, just think of it as like an ID tag for a particular person in the population. And this notation is just saying, take this measurement for that person. What's that value? So this is a number. This is a particular number that's like the height of person number 2. And this concept, expectation, is often notated like this with the E bracket X. And you can also, this notation that I've written up here, you could, if you wanted to, write it like this, where you have 1 over big N, sum from 1 to big N of X of omega I. This is exactly the same thing as I've written here. It's just a little more compact notation. You don't have to do the dots, which is a little hand wavy. This is just saying sum up the heights of all the people from 1 to N and divide by N. And the reason I have this in quotations here is because with this definition that I'm showing you, it's giving you the right intuition. It is a population average, but there's many cases in which the population is not finite, right? Or shouldn't be necessarily imagined as such. And so this notation does not actually make sense. You can't add up an infinite number of finite values and divide by infinity. So this is not a totally formal definition that can be applied in all cases, but it is the definition that I want you to think about and reason with when you're doing problems with expectation, because it will give you all of the right rules. And using the more formal mathematical definition that works in, more when the population isn't finite, or when you're talking more generally about distributions, whatever, it's not necessarily going to give you the right intuition, but you are going to get all of the same rules out of it. And to learn it, you need to kind of understand more calculus and things like that. But there's really no need to, right? You can get everything you want, all of the intuition out of expectation that you need for this course, you can get by imagining a finite population, and you're just taking the average in that large finite population. So when you see this symbol down here, EX, this is saying take the big E bracket is saying take the population average of, and then the thing in the bracket is the measurement that you want to average. So if X is age, this is the average age. But if I had Y and Y were representing height, then this would be the average height. So that's just a little bit of notation. And in terms of terminology, these things all mean the same. So population average means the same thing as mean. If you see people say mean, they're almost always referring to population mean. And that's the same thing as expectation. These are all the same. Of course, these are all, technically you need the population average of some measurement, the mean of some measurement, expectation of some measurement. But if the random variable in question is clear, then the meaning of this is clear as well. So expectation is different from the sample average. So somebody might say population average versus sample average. What's the difference? The difference is that, as we've described, the expectation is a population quantity, and the average of some numbers is a sample quantity. So this is a number. This is some fixed number. It's out there. You may not know what it is, but it's some real number. That's the average height, for example, of everyone in your population. Whereas the sample average is the height of the the average height of the 100 people who you chose to sample. This quantity, which we'll talk about more I think next week and the week after, quantity is actually random, because the sample that you get is not a priori known, right? You're going to get 100 random people from your population. You don't know before you start making calls who you're going to get there. And so if you do this and somebody else does the same thing, you're going to call up different people. You're going to get different samples. You're going to get different sample averages. So the expectation is a fixed number. It's ground truth. It's what we want to know, but we don't. The sample average is a random number that we're going to get once we run our experiment or survey or whatever. That is in some way an approximation of this true fixed expectation. But your mileage may vary over here. Okay. Right now, we're going to get to this more, talk about inference later, but right now I just want to focus us on understanding the properties of this kind of a ground truth, because we're going to use those, the ground truth expectation, because we're going to use those later in the course to build up the ideas of like risk ratios and causal effects And that's all. And to understand what we can say about those things based on particular assumptions about independence and whatnot. But first, we just need the tools to be able to know what we're talking about. So again, this is just exactly the same thing that I have on this slide. I'm showing you more concretely in code. You might imagine you have some population data set. It's some really large data frame. If I take that population data set and I take the mean of a variable x within it, that's the expectation. But in the real world, what we most often have is some subset of little n people from this big N size population. And the sample average is the mean of those little n people. So if you take this code and you run it on your computer right now, like just set up, put whatever you want here. So get some, if you want, you can go to the first lecture and use that fake New Zealand data set, right? Let's say it's like 5 million rows, right? If you then run this code and hit enter and then do it again, you're going to get two different numbers because this slice sample function is not always sampling the same n people. So that's what I mean when I'm saying that the sample average is a random number, because you're not going to get the same answer if you do it twice. Okay, so there is a connection though between the sample average and the expectation. As you might expect, if you start sampling more and more and more people from your population, the sample average on average will look a lot like the expectation, which is this true fixed number. So we can leverage that and get a very good approximation of the expectation. We'll make this a little more rigorous later, but we can get a very good approximation of the expectation if we can sample very large numbers from our population. So here, for example, I'm generating a normal random variable that has true mean of 0. So our norm, right? Here I'm generating, what is this? Like a million or 100,000 observations of a normal random variable with mean 0. And I'm just averaging those 100,000 observations. So this is a sample average, but it's a very large sample. And the number that I get is very, very close to 0, which is in fact the true mean. If I could draw the entire population, which is infinite, but again, this is the intuition. So a little more intuition now, maybe visual intuition about what the expectation is. So if you are thinking in terms of density functions, so this is for a continuous random variable that takes values between -infinity and infinity, and you create the density function. If you want to think of the density function as like, you take all your people in your population and you tell them to stand along this line, depending on what value of x they have, right? It's going to be something like this. We're going to get a lot of people standing for this random variable, this population. We have something like this, right? Where we have a lot of people with values near x equals 0, and then it's quite rare to see people that have these much larger values. So if you were to stack people up like this, the expected value of this measurement is where you can kind of balance this density function. So if you think of this density function as like a physical object, like a piece of paper that you kind of cut out, right? You cut out this shape, and then you're trying to balance it like you do like a ruler or something like that. The point at which you put your finger underneath this curve is the expectation. So in this case, it's 0. That's where I have to put this fulcrum in order to balance the two sides of this against gravity. So here's another example. This is another density function. This one is bimodal. So in this case, we have a lot of people, whatever this measurement is, we have a lot of people who have values near 0. And then every now and again, we get some people who have values near 20. So you get this two-peak distribution. And in this case, the expectation is about here. I think this is like, 2.5. And the reason it's here is because even though there's a lot more people with values near 0, the people with values near 20, because they're so far away, they really are kind of tipping the scale. So again, physically, if this doesn't make sense to you, maybe find an object like a ruler or something like that, and if you put a big weight near where you're balancing your finger, and then a little weight, you can actually balance out that big weight with a tiny weight if you put that tiny weight pretty far away, because it has a large lever arm that's pushing down on that. So expectation, again, it's kind of where you have to balance the mass of such a density function. You can also have kind of funny things because the expectation can be a value that the random variable itself cannot take. So here's an example. This is the density function for a coin flip, right? 50% of the time I get tails, so 0 mapping to tails, and 50% of the time I get 1, which is heads. So I can't flip a coin and get a value. If heads is 1 and tails is 0, there's no universe in where I get a value of 1/2. I'm only ever going to get a 0 or 1, right? However, the expected value, the population average of all the coin flips, if half of them are 0 and half of them are 1, then I'm going to get a bunch of 1s. Looking at this formula here, right? I'm going to have 1, 1, 1, 1, and then 0, 0. So for every 1, I have another 0, right? So this total up here is going to be big N over 2, and the total underneath is going to be big N. So the expectation is 1/2, okay? And 1/2 is here. My random variable cannot take that value. There's nothing wrong about that. I'm just trying to show you that the expectation quantity does not necessarily have to be a value that can be that the random variable itself can take. It can still be the expectation of that random variable. That's totally fine. Okay, so hopefully that's some good intuition. Now let's. I gave you the definition of expectation in terms of the population data, how you can just average the value of this variable. Of course, we know that population data are not a real thing, and we most often abstract population data by instead talking about what's the distribution of some random variable. Imagining that this random variable has some distribution or is jointly distributed with these other random variables. And then we can define things in terms of the density function often. So I'm going to show you how to define expectation in terms of densities here. So let's say that this is my population data set. And again, a very artificially small population. I have 5 people, and I've named them A, B, C, D, E. The little omega, again, you can just think of it as like a name tag. And then the value that of x for each of these people is 1 for A, 2 for B, and so on and so forth. So down here, what I'm showing is calculating the population average kind of by brute force, right? I'm just adding up all the values of the random variable, and I'm dividing by 5 because there's 5 people. Now, here what I'm showing is I can group, before I do that sum, instead of just going A, B, C, D, E, I can actually group these by what value the random variable takes. So here's the group of people who have x equal to 1. And here's the group, so A and D. And now the people who have x equal to 2, that's B. And now the people who have x equal to 3, which are C and E. So this sum, I've just reordered the terms here. So I have 1 plus 1 plus 2 plus 3 plus 3, and then still over 5. It's all the same. And now, since I have 2 1s, instead of writing 1 plus 1, I can just write 2 times 1. And since I have 2 3s, instead of writing 3 plus 3, I can just write 2 times 3. So really all I need to know is how many times does this thing happen, and what is the value of x when that happens. So x equals 1 happens twice, x equals 2 happens once, x equals 3 happens twice. So you can see I don't care about who was who. I don't care about who's A, who's D, who's E, whatever, to calculate expectation. And now I can just divide 2 by 5, 1 by 5, and 2 by 5, and write it like this. So it's 2/5 times 1, 1/5 times 2, and 2/5 times 3. And what are these numbers? These numbers are exactly the probability that x equals x. It's how many times did x happen divided by the population total, and that's exactly the probability that x equals x. So I have probably x equals x. And what is this? This is exactly the density function here. So this is the density function for x, and this is x. And what this shows you is another way to write the definition of expectation, which is like this. So what we see here is that we can write So this is f of 1, and then this is times 1, and then this value here is f of 2 times 2. And let's go back so you can see that. So f of 1 is this 2/5. So because if I put x equals 1, then the value of f is 2/5. If I put x equals 2, the value of f is 1/5. So this is f of 2. And then we're adding these together. And then here's f of 3 times 3. So we just need a formula that iterates through the values of x. So here x is 1, x is 2, x is 3. And multiplies f of x times x, and then adds up all of those values. And that is exactly what this is telling us to do here. So here we're adding up over all the values little x that big X can take. So in this case, big X was either 1, 2, or 3. So there's going to be these 3 terms showing up. And then we compute the value of the density for that little x, and then multiply it times the value of x. So another way you can think of it is that we have the value that the random variable takes times the relative number of times that it takes that value, and then you sum up over all possible values. Okay, and this is exactly what we've done up here. You can see it's completely equivalent to just taking the population average. It's just that we've done the averaging instead of kind of brute force. We've first done sub averages, and then within this, we've broken it up, right? Into people who have the value 1, among whom the average is going to be 1, right? And then, so these are kind of like the sub-averages, and these are the probabilities of being in each of these groups, and then we're averaging those together. So this is the same. It's an equivalent definition that you can use, but this definition is in a way more formal than the one I gave you before, although it's a little less intuitive. But it's more formal because here you don't need to have a population data set in mind, right? You just need to know what the density function is for this measurement. So now I'll show you this, which is the same definition, but this one can be used when x is a continuous value. So in the example that I gave before, here, big X was a random variable that could take 3 possible values, 1, 2, or 3. Now, if X can take any value between 0 and 1, for example, or minus infinity and infinity, then this discrete sum doesn't make sense because, for example, if you're going from 0 to 1/2, then you're skipping all the numbers. You're skipping 1/4. If you go from 0 to 1/4, then you're skipping 1/8. So you have to continuously sum over all these numbers. And so we have to replace this sum with an integral. Again, if you're not familiar or your calculus is a bit fuzzy, that's okay. It doesn't matter. You can get all of the same intuition and understanding from thinking of it as this kind of sum. But if you're actually going to do calculations with these things, you need to do the integrals. But it's the same kind of idea, right? You're summing over all possible values, taking the relative number of times that the random variable takes that value, multiplying it by the value that the random variable takes. So what are the expectations for some common density functions? So if we have a random variable that has a normal distribution with parameters mu and sigma, you might recall that these parameters are in fact called the mean and the standard deviation. It turns out the expected value of x is this mu thing, that's why it's called the mean. Because it happens to be the mean. So is this magic, right? Or why is it like this? Well, if you wanna figure this out, all you need to do is apply the definition from the previous slide. So remember that when I say x is normally distributed with mean mu and standard deviation sigma. By the way, I guess good a time as any. Sometimes people will parameterize this as mu, and then they'll tell you that whatever number is here is sigma squared. Sometimes it's sigma, so just be aware, because if you see like normal 0, 2, right? Does that mean that sigma equals 2, or does that mean that sigma squared equals 2, which would imply that sigma equals square root 2? So you just got to know which convention people are using. I think this one is more common, although I think in my slides I use this one, but you'll see both. So just keep in your mind that this is something that you should be aware of. Okay, but coming back here, if you see this, what does this mean? That means that the density function for x is, and you don't have to have this memorized or anything, you just look at Wikipedia or whatever, but I've been doing this for a minute, so I happen to know that it's pi sigma squared, I think, in here. E to the minus x minus mu over sigma squared. Okay, so this is the density function. So how do I know that this thing is mu? Well, I can say, well, then what's the expected value of x? Well, the expected value of x, from our definition on the previous slide, is the integral of this function times x dx. And so if you go to Wolfram Alpha or ChatGPT or whatever, I mean, you can also crank this out if you want to practice your, Math 1B or whatever calc class you took skills way back in the day. But so here's the x, and then the f of x is the rest of this stuff that I'm putting here. Blah 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 blah, dx. Just crank through it, and you'll see that the number you get out is mu. And this is actually not like a trivial integral. It's like kind of gnarly, but Wolfram Alpha can do it. Whatever. I don't know how to integrate shit anymore. But you can see that it actually does follow from this. This one is a little easier to see. So Bernoulli, when we say if that x is, what does that mean? That means that the density is 1/2 when x equals 0, and 1/2 for x equals 1, right? This is the density function for a Bernoulli random variable, which is modeling a coin flip. So x can only take two values, 0 and 1. So here we can apply the discrete definition of expectation. Oh, so actually, sorry. So this is a p. This is a generic p, not a 1/2. So if there were 1/2, it would be 1/2. But for a generic p, well, and we're saying that x takes the value 1 with probability little p, and otherwise x is 0 with probability 1 minus p. Because if it's not 1, it has to be 0. So the probability has to be 1 minus this probability. So for example, this is like representing a coin flip where there's some bias, and 3/4 of the time you're getting heads, 1/4 of the time you're getting tails. So what's the expectation? We can work it out using our formula. And in this case, what is this this sum here, right? X only takes two values, so this is summing just over these two terms, 0 and 1. So let's just plug those things in. So this is just a shorthand for f of 0 times 0 plus f of 1. Geez. There we go. Plus f of 1 times 1. And now we just plug those values in. F of 0 is 1 minus p, but it doesn't matter because it's times 0. So this thing is going to be 0. And now this is f of 1 times 1, which is just f of 1. So f of 1 is equal to little p. So that shows you how we go from here to here, just from calculating based on if we know the density, we know the expectation. So why does that make sense? Because the density is telling us what it's effectively a stand-in for the population data, right? And the expectation is the population, the average of the measurement. And so if you know the population, you know the expectation. Similar here, right? If you know the density, you know the expectation. This is just the more kind of formal way to do it. And the last one, which we haven't talked about, is a uniform distribution. So here L and U describe the bounds. So this is like if you have L and U, this density looks like this. So This is describing a random variable where it's like take a random number between L and U. And all values between L and U are equally plausible. So the standard uniform is between 0 and 1. So just give me a random number between 0 and 1. The expectation of this, we can integrate, actually. I'll show you how to do that, might as well, to work through it. But you should also just be able to see visually from this picture. If you think about the kind of visual intuition that we were describing earlier, the density here is just like this. It's this box, and it's 0 everywhere else. So if you think about where can I balance this box, right? It's actually going to be exactly in the middle, right? It's going to be exactly in the middle because there's going to be more weight on one side if I move this over, because every part of this box weighs the same amount. And what is this middle value? It's exactly 1/2 of the way in between L and U. And that's this expectation here. You can also do this integration. So this density function is given by, so the total area here has to be 1. This distance is U minus L. So this height has to be 1 over U minus L. So the density, overall the density is, it's 0 unless you are between L and U. And when you are between L and U, the value is 1 divided by U minus L. Okay? And then you just want to integrate that, times x dx. Let's see what we get. So this U minus L, let me just make sure that, yeah. So that can come out because that's just a constant. Again, don't trip out if you're like, I don't know what the hell you're doing. What's integral, whatever. I'm just applying the definitions. And if you see this, you can take a screenshot of that. You can write it out, take a screenshot, put it in ChatGPT. It'll tell you how to do this. The integral is kind of like area under the curve of a particular function, and in this case, the function that we're integrating is this whole thing, x times this indicator function. So if this is 0, I can also write it again for people who are familiar with calculus. You can follow along. Otherwise, don't worry. So this is just a function that's 1 when x is between L and U, and it's 0 otherwise. So this is the same as just the integral from L to U of x dx. So in terms of a plot, here's L and U, and we're interested in this area here, which you can do it analytically or geometrically if you break it up into this box, and which has height L, and so it's L times U minus L is the area of that box, and the area of this triangle is U minus L is the height, and then that squared divided by 2. Okay, so I don't know. Let's just see where we're going here. So this is that area there. You can also do this. I think the calculus way. Say the antiderivative of this is x squared over 2, and then you evaluate that at L and U. So this sum will be the same as U squared over 2 minus L squared over 2, which is 1/2 U minus L. So U squared minus L squared is U minus L times U plus L, because we got the minus L squared here. So the one that cancels is this negative with that constant, and what we're left with is just that U plus L over 2, which is what we got there. Cool. All right, we can do math. So you could have just skipped all that and still pretty much come away with the same thing. I'm just showing you how it's just like a brute force application of the formula to derive what the expectation is given the density. If you know the density, you can get expectation. I'm not going to really ask you to do that. I just want you to know. I may ask you to practice it like once or twice. But this course is not really a lot about working with densities. You just need to understand what they are, and the fact that if you have the density, it's the standard for the population data, you can get everything you need from there. So let's do this example here. So we can create this table, which represents a population data set in R. So there's going to be 1,000 people in this population. I'm giving them each a name tag, 1 to 1,000. And the value of my measurement x is going to be 0 if the ID tag that you get is even. It's going to be 1 if your ID tag is divisible by 3 and not even. And if none of that is true, you're going to get value 2. So the question is to compute the expectation of x directly, and then first to do it by creating a table that represents its PDF. So when I say directly, I don't mean analytically with formulas. I mean you have the population data set, right? So you can actually just brute force compute it. So let's give this a try. Type this into R yourself. All right, let's have a go. Okay, let's generate it. Sure. And now we can make our data. Okay, so we have a population data set. You can see here's the ID tags, if you want to think of it like that, and then the value of our random variable of interest. So we want the expectation of that random variable. That is just the mean in the population data set. So since we have the population data set, let's give it a name. Okay, and we can just do this. Oh. Okay. So the mean value of x in this population is about 0.833. Well, exactly 0.833. Okay, so now I want to first create a table that represents its PDF, and then calculate expectation. So I'm kind of asking you to follow the steps here. So how can we first create its PDF? Let's group by x, and then so I'll call f the value of the density. And I want that to be the total number in that group. You can get that with the little n. So it's the total number in that group. Let me just show you what I mean. Capital X. Okay, so these are the counts. So if I want to have a proportion instead of a count, I could do like this, I think. Yeah. So a little bit of a syntax, our syntax thing. And there's other ways to do this. You can do it in many different ways. Okay, code-wise. But what this says is take the number of rows of dot. Dot in the tidyverse is normally a little placeholder that refers to the argument being passed into the function that the dot is in. So this whole thing, right, is being passed this data frame as an argument, the data frame that comes from here. So when I say nrow dot, it's the number of rows in this data frame, which is however many people there are in the population in this case. So I could have also done like big N is equal to nrow population. Okay, and then like this, and you get the same answer. Okay. Point being, we now have the density function for this random variable x in this population. And we've gotten rid of the, abstracted away the population data set. We don't need that. And my question is, how can we calculate the expectation just from this? So before, if we had the population data set, we saw we could just, do this. But now with just this density function, what can we do? And if you've been paying attention, you realize that what we can do is sum up the values of x times the value of f. So the notation looks a little bit different here than it does mathematically, or maybe I'll reverse them because in the slides it had f times x, but it doesn't matter. So here, x is the value that x takes, and then f is the relative number of times that f takes that value. So I don't have to do f of x because here I'm representing f as this column in the data frame. It's not a function. I could do it as a function if I wanted to. I'll show you that in a second actually. But this is giving me the same thing. Okay. So if I were to write it as a function, so I could write maybe like f is equal to of x, and then, well, first I need to get the density table. Let's do it like this. Yeah, did you guys know you could do this? It's totally cursed. You can assign that way. Okay, so now I have density table, and I could write a function of x, f is equal to function of x. What do? I just go to density table, and I get out the value where x equals x, and then I give you back whatever is in the f column there. So now I can do like f of 0, f1, f of 2, okay. So now I have this function that returns the value of the density. Instead of pre-computing it and pulling it, I could just like go to the population data set and count every time. So again, there's many different ways to do this. And the only purpose of showing you this is so that I can give you this kind of notation. So now what I want to do is f of x times x, and then I want to sum over x in 1, 2, 3, something like this, right? So the way to do that, I'm just going to type that so it can stay there, is with the map function. So yeah, let's do it like that. Why not? So 1 to 3, and then here we can put x times x. This is kind of magic. Oh, sorry. Okay, that. Okay. Is there? Oh, it's not 1 through 3. Sorry, it's 0, 1, 2. Okay, so let's back up here. 0, 2, 2 are the possible values. Run this. Okay, so that, and then all I need to do is sum those up. Same thing. Okay. So here, this is really roundabout way. I'm just trying to get you to understand that of doing it right. Like I had already done it this other way with this table, and I just multiply the two values in the columns and sum them up. This way, I'm just showing you that I can do it where f is not a column, but an actual function where I pass in the value of x in. But it's the same thing. Hopefully that's clear.